Okay, so now let's look at chapter 4, clean room, wafer cleaning and gettering. So here's the the defect on the contamination on the semiconductor industry. So here up to the year 2012, usually the dust particles that is half of the minimum feature size will make it will cause the trouble. For example, when we have for the 50 nanometer minimum feature size, the particle size of 25 nanometer will make the device not working. So now we know that now today it is 5 nanometer. So that means any particle, almost any particle in the air will kill a device if there is one on the device surface. So this is what is called the LLS. It's called the localized light scatters. This uses the light to see how many particles there is. So this is why you can see 0.015 per square centimeter. This is why the GOI is the gate oxide integrity. So this is measure the gate oxide, whether there is any defect or not. So this is why we need to be less than 0.01 defects per square centimeter. So normally a chip is like 6 square centimeter. That means within a chip size, within the CPU size, there will be well below 1 defect. So this CPU will work. So this is memory. This is logic. This is CPU. This is memory. This is the CPU. 0.03. Then is the metal contamination. In this case, the metal contamination needs to be less than 10 to the power 10. After cleaning, should be less than 10 to the power 9. So this big number or small number. So we compare this number to the number of silicon per area. We want to compare this number to the number of silicon atoms per area. So how to calculate this? So we need to look at the silicon structure. So here is the silicon lattice structure. You can see at this level, so we have 2 atoms per unit cell. So one from the corners, one from the middle. At this height level, so we have 2 silicon atoms per unit cell area. So at this height level here, so we also have 2 silicon atoms. At this level here, so we have half on each face, half of them on each surface. So we also have 2. The same thing for the other levels. So that means the number density per area is given by 2 divided by the unit cell area. So the unit cell is 5.43. So we come here again. So the silicon atom is given by, so we have 2 atoms. As we see, we have 2 atoms per unit cell divided by the area of the unit cell, 5.43 10 to power minus 8 centimeter area. Then will give you 10 to the power 15. So we have 10 to the power 15 atoms per square centimeter. So you can see the impurity, 10 to the power 9, is very small compared to the number of the silicon atoms per area. Then the recombination left hand. This is what is recombination? So electron and holes. This is electron, but this is hole. So they come together. This is called a recombine. So usually when there is impurity, electron and hole, they will recombine more easily. So if the left hand is higher, that means we have less impurity. So this is the type of the contaminant. So we have the particles. This is the main contaminant. So most of the device is dead because of the particles. Organic films, photoresist is also organic, heavy metals and alkali ions. For the ions, this has the charge. This charge will shift the threshold voltage. It's given by this formula here. So we have known that. So normally, so the threshold voltage is given by this term. So with actual charge, QM, this is the charge at the interface. gate. So here is this is the channel oxide. So this is the gate. So this is oxide. So this interface here, if this interface here has the charge, then will shift the threshold voltage by this amount. So this is similar. This is similar to what we have seen in chapter 2. So if we look at here, so here we have this term here. We have this term. This is the threshold voltage adjustment from chapter 2. So this term is very close to what we have seen in the previous slide. So this QI, so this is the implanted dose. So this is the dose implanted into the silicon. But for this here, so for here, so the dose here is at the interface, is trapped at the interface between the silicon oxide and the silicon. So here has the same effect. For example, if the gate oxide is 10 nanometer, but now this is no longer thermal oxide, it is the high K material, then 0.1 volt threshold voltage shift can be caused by sodium or potassium ion of this number density. You can see 10 to the power 11. So this 10 to the power 11 is much smaller than 10 to the power 15. That's why this is a very big effect. If you remember the quiz, question, so in the 1960s, the MOSFET was not utilized commercially in the 1960s because there is always a charge at this interface. So this charge here makes the threshold voltage not stable. So later on, people realize that so the alkali ions like sodium from our body, sodium from the hand, so this will kill the device. And now let's look at the clean room. So to get rid of the contaminant, so we use the clean room, clean factories, wafer cleaning, and gettering. So now we look at them one by one. The first, clean factory or clean room. So in the clean room, so we use the HEPA filters. We use the filters to circulate the air, to filter out the particles. So this high efficiency particulate air. So we have this contains lots of thin porous sheets of the fibers. It can get rid of most of the dust particles. So the room air is forced through the filter at 50 centimeters per second. A large particle is trapped. A small particle stick to the fibers by the electrostatic forces. So the air coming out of this HEPA filter is better than class 1. So we will look at class 1 later on. And for the workers, we wear the bandit suit for the workers, and the gas and the chemicals are filtered, and we follow the manufacturing protocols. Now let's look at the definition of the class of the clean room. So the air quality is measured by the class of the facility. So defined as 1 to 100,000. This means the number of the particles higher than 0.5 micrometer per cubic foot of air. For example, if we look at here, so class 1 means the number of the particles bigger than 0.5 micrometer is 1. The bigger than 0.3 micrometer is 3. Bigger than 0.1 micrometer is 35. This class 10 and class 100, etc. Here, so the drawing is the same thing. The class 1, so this is this one here. So this is 0.5 micrometer. So class 1 equal to 1, class 10, 10, class 100, class 1000. So there are more particles with smaller sizes. So for me, I think today the clean room is class 1. For me, I have visited clean room with class 10. So at University of Waterloo, the quantum nanofab in the QC building is class 100 for the lithography room and class 1000 for other rooms. The typical office building is about class 100,000. So the particle size that is most concerned is 10 nanometer to 10 micrometer. Smaller particles, they tend to coagulate. The larger ones will precipitate onto the ground. So the particles deposit on the surface the particle deposited on the surface by the Brownian motion. So Brownian motion is that the particle is pushed around. The particle is pushed around by the molecules of the air molecules like nitrogen molecule, oxygen molecule. They push around the particles. This is the Brownian motion. The larger ones, the gravity will be important. So this one, the definition is a cubic foot. So we know that. So this is not international unit. This is like American unit, a foot. The international unit we use how many cubic meters. So for the international unit, so we don't use foot. So we use ISO 875. This is clean room classification. We know that, for example, you look at here, this is the conversion. ISO 3 corresponds to class 1, class 10 ISO 4. So you can see this is the IS class 1. So this is per cubic, 1 particle per cubic foot. Then this corresponds to 35 particles bigger than half micrometer per cubic meter. So 1 cubic meter equals to 35 cubic foot. So in this clean room, so this is the number of air changes per hour. For example, for the ISO 5, this is class 1, I think. ISO 5, class 100. So ISO 5, class 100. For class 100, so the air is circulated 300 times per hour. And that means every 10 seconds, about every 12 seconds, the air is fresh air. It's fresh air in the clean room. So another thing maybe I can also show you is so this is the particles. If you care about air pollution, you know this thing. So PM 2.5. So this is the air pollution. So this is air pollution. In Canada, there's not a problem, but in China, you know, the air pollution is a big problem. A big problem in China. So what is the PM 2.5? So PM is particulate matter. So if we look at here again. So this is the particulate matter, the PM. Particulate matter. So PM, particulate matter. So PM 2.5 means the diameter of 2.5 micrometer or less. So the diameter 2.5 micrometer or less. We also have PM10. PM10 means the diameter, the particles diameter 10 micrometer or less. So the unit is how many microgram per cubic meter, I think. Here you can see. So allowed, so this is in China. So this is the unit for the PM 2.5 is how many microgram per cubic meter. How many microgram, that's the particles in air per cubic meter. This is the air pollution. It's also about the particles. But here is the mass. How many grams? So here's how many numbers. Here's how many grams. So generally, the particle size will kill the device when they are close to the device critical feature set of the device. The 75% of the yield loss in the VLSI, very large scale integrated circuit fabrication facility, is due to the particle contaminant. So the critical size is 0.1 to 0.3 micrometer. So larger one, as we mentioned, larger one will precipitate, small one will agglomerate into the larger ones, as you can see here. So when the particle is bigger than a certain size, then the particle will cause the yield loss, yield loss. But this depends on the feeder set. So this one you can see is about maybe 0.4 micrometer. This is like 10 years ago. Nowadays, every particle few nanometer will kill a device. So now let's look at the wafer cleaning. So the cleaning, so we remove the particles and organics and metals from the surface. So particles is mainly removed by the ultrasonic agitation. So all the clean room, so we have ultrasonic cleaning. Organic follow this, so they are burned away by the oxygen plasma or by the very oxidizing solution like Perina. And for the industry, the standard clean is the RCA cleaning. A cleaning normally we use robot because the human body can emit 5 to 10 million particles per minute. So this is the standard wafer cleaning process for the industry. So first, it uses the Perina, the mixture of sulfuric acid and hydrogen peroxide as the 3:1 or 1:1 ratio at high temperature. So when we mix them together, because when they are mixed, they got heated up. So we know that both sulfuric acid and hydrogen peroxide, they are very oxidizing. And high temperature, this will burn away the organics and photoresist. So then we use HF. HF will etch away silicon dioxide. Silicon dioxide will be etched away by the HF. So when we etch away the silicon oxide, so all the contaminant on top of the silicon oxide will also be etched away. So then we rinse with water. Then we use this called RC1. We also call it RCA number 1. RCA cleaning number 1. So this one will remove organics and metals and particles. So we will look at this one and this one in next slide. Then we rinse. Then we use RCA SC2. Then we rinse. So RCA is the radio corporation of America. So this has to be a really big company. So RCA, you can see this is RCA history. So this company has been the dominant electronics and communication companies in the United States for 50 years, from 1920 to 1970s. In the 1960s, it also worked on the integrated circuit. That's why they developed this RCA cleaning process. But today, this company is dead. This company was dead in 1985 or 1986. But today, you can still buy the RCA brand TV from the supermarket. But it's only the brand name. The company is already gone 35 years ago. So now we look at the RCA cleaning step 1 and step 2. So this is step 1. So we use this is step 1. So we use a mixture of the hydrogen peroxide, ammonium hydroxide, and water. It's diluted at a high temperature for 10 minutes. This high pH, so this one, so we have this hydrogen peroxide, so this will oxidize organic contaminant. And for this one, it will form complex with those metals. When they become the complex like this is soluble. And this one, because of this, it also dissolve the native oxide and grow back new oxide. This process will remove particles on top of the oxide. But this process, dissolve native oxide and grow new oxide, can dissolve again. This means it etch silicon. So the surface will become rough. So nowadays we use less ammonium hydroxide. So this is HC1, RCA cleaning step 1. So this one is standard cleaning 2. So here we have the hydrochloric acid. This one ammonium hydroxide. Then we will still have the hydrogen peroxide and the water. This one can remove alkaline ions and cations like those cations that cannot be removed from the previous step. So those things, they form the precipitate on the wafer surface from HC1, but they will be removed by the HC2 process. It also removed the metal contaminant like the gold. So through the cleaning process, we can also do the ultrasonic agitation. So this will remove the particles by the shaking. So ultrasonic is to remove the particles. We know that for the sound, it is 20 hertz to 20 kilohertz. But this is the sound. Higher than 20 kilohertz is ultrasound. So normally it's 20 to 45 kilohertz. We have this high frequency sound. It will called cavitation, and form bubbles, vapor bubbles. The bubble is form, break, form, bubble, break, bubble. So this process is mechanically scrub the surface by the bubbles. So this is okay. This is effective to remove particles higher than 0.5 micrometer. So nowadays people also use microsonic cleaning. This can remove particles less than 0.5 micrometer, but still microsonic is not as popular as the ultrasonic. And also we use DI water. DI means they ionize the water. That means there is no iron in the water. This is DI, but there may be some organic contaminant in the water, but just no iron. So because we know that, so those ions, they are really bad for the device. So we need to get rid of this sodium, those ions. So this is done by making the DI water. So they use the RO process. I think it's called reverse osmosis, something like that. Filtering, RO, reverse osmosis filtering process to get the DI water, get rid of the ions. So when there is no ions, the resistivity of the water should be bigger than 18 megohm centimeter. So actually, the clean room, they measure the resistance constantly. They measure the resistivity constantly to make sure that the DI water works well. So how we get this number? So we know that for the electron and the hole and host, for the carrier electron and host, the resistivity given by 1 over n mu e mu e plus p e mu p. So we know about this from chapter 1, right? The resistivity. So here is something similar. So when we have the water, there will be ion, hydrogen ion and hydroxide ion. So those ions will contribute to the conduction of the water. At the room temperature, the ions is given by this number here. So we know the ion, this corresponds to the N and P, and we know the diffusivity D. So we will talk about diffusivity in chapter 7. In chapter 7, we'll talk more about the diffusivity of the dopant, chapter 7. For the case of hydrogen ion and hydroxide ion, the diffusivity is given by those numbers. Then we can use the Einstein relationship, find out, if we know the diffusivity, we can find out the mobility. The mobility is given by those numbers. So once we know the mobility, we can find out resistivity like this. So it's the charge Q, carrier concentration, mobility, given 18.5 megohm. So normally we need it to be higher than 18 megohm. Then we know the DI water is good. So now we look at the third cleaning step. It's called gettering. So this word I think is very new to all of you. So gettering, you can think this means get rid of by trapping. We find a way to trap. We trap the contaminant. For the alkaline ions, the gettering generally we use dielectric layer on the subset. For example, we can use the PSG. To trap those alkaline ions, or we can use the silicon nitrate to block them getting into the device region. So PSG means phosphosilicate glass. That means the glass contains 5% of phosphorus. So this is called the PSG. It's done by the LPCVD. It's coated by low pressure CVD. So we know that for the silicon oxide, it's coated by using silane gas, right? We use plus oxygen at high temperature to form silicon oxide. This is LPCVD, low pressure CVD to form silicon oxide. If we add phosphine gas, P3, we add the phosphine gas to here, then we can have the P2O5. So we can have P2O5, then we have the PSG. In chapter 2, so we also talk about BPSG. That is boron. The B means boron phosphorus silicate glass. We have to use BPSG, but here is the PSG. So this one will trap the alkali ions. So for the metals, we use the gettering. But you traps the metal ions. So because the metal ions like gold, they do not fit in the silicon lattice. So they prefer to stay at the defect site. So that means if we create a lot of defect, then those metals will be trapped at the defect. So the defect can be created at the backside. This is called external gettering. So we can make the backside rough, damage the backside of the wafer, or deposit some polysilicon on the backside. So we have a lot of defect on the backside. This is called external gettering. We can also do the bulk, intrinsic or internal gettering. So in this case, the defect is inside the silicon wafer, not outside, not at the backside of the wafer. Then if we can have defect in the wafer, then it will be trapped inside deep inside the wafer. So here are the impurities. So those are the shallow acceptors and the shallow donors. This is what we want for the doping. The shallow means here. So this is the conduction band. This is the valence band. This is the shallow, very close to the conduction band donor. This one is also shallow. Very shallow. That means very close to the valence band. This is the acceptor. This is what we want. And those alkali ions is very bad. We know this will. But alkali ions will shift the threshold voltage of the transistor. This is very bad. So those impurities here, this is called deep level impurities. And they are also very bad because deep level means like this. This conduction band, this is the valence band. This is the deep inside, between far away from the conduction band and far away from the valence band. This is called deep level impurities. They are bad because if we have electron here and if we have a hole, electron and hole, they come to those deep level sites get recombined. But when the electron hole they got recombined, this will make the electron and the hole lifetime very short, recombined. If we look at the physical space, maybe something like this. So here you have the ion atom here. The electron move here and the hole move here. So when you have ion here, electron come here, hole come here, they got recombined at the ion site. Something similar to what you see here. So this trap is very bad. So how to trap them? So how to trap those impurities? So we know that they prefer to stay in the defect. So the idea is to have the defect, and then we move them around to the defect site. So here is how far it moves. This is done by the diffusion. This is the diffusivity. So diffusivity, centimeter square per second. So of the different materials. Here is the temperature. So higher temperature, higher diffusivity. And this one is the log scale. So what is the point of this? For example, if we have say we have gold here, we want it to move to the backside of the wafer. We need to move a few hundreds of micrometers. So how do we know whether the gold can move hundreds a few hundred micrometer far away. So this is given by the diffusivity. So you can see silicon has low diffusivity, so that's good. We want silicon to be fixed. So those dopant, they are all substitutional. The diffusivity is also very low. So this gold here, so we have here S means substitutional, so also low diffusivity. But this one here, I means interstitial. This means higher. They give you much higher diffusivity. So those metals here, gold, iron, chrome. You can see at high temperature, they have diffusivity higher than 10 to the power minus 6. So the distance traveled given by square root of dt. So we will look at the diffusivity in chapter 7. So here we just get the numbers. So 10 to the power minus 6 times. Every time we talk about a thousandth second, but then give you 10 to minus 3 centimeter, 300 micrometer. So that means the gold, normally the wafer thickness, usually the wafer thickness is like 700 micrometer. You can see this is comparable to the wafer thickness. That's why I mentioned, so those impurities, they can travel from one side of the wafer to the other side of the wafer and get trapped there. At the other side. So this is the idea of the trapping. So because those impurities, they can move around far away. Here is the gettering process. So on the top we have this phosphorus silicate glass layer to trap alkaline ions. So the device here, the transistor, is on this layer here. Now this part is called denuded. That means no defect, no oxygen. So no oxygen, no defect in this denuded region. Because we have a device here. We want to keep this area here to be clean. So they call it denuded. The inside of the wafer, in the bulk of the wafer thickness, we have this intrinsic gettering region. So the impurity, they move, get trapped here. It can also move to the backside of the wafer. So this is called extrinsic backside trapping. So the thickness, the wafer thickness is higher than 500 micrometer. So here the gettering consists of 3 steps. The first one is the making metal atoms mobile. So making the metal atom mobile. So this can be done by making the metals from the substitutional to the interstitial. For example, if you have gold here, so silicon. So this is the silicon. And we have to have silicon here. So this silicon here, this silicon atom here is called the interstitial silicon. So if we have this one, so they will exchange the space. That means this silicon here will come to here, and this gold will come to here. So once the gold atom comes to here, it become a interstitial. The gold become a interstitial gold, from substitutional to the interstitial. So once it become interstitial, it can migrate very, very fast. Then they got trapped at the defect site. So now let's look at how to make the defect. So this is done by the intrinsic gettering. How to make the defect? The defect is made around silicon oxide precipitate. So we know for the silicon, so we have a lot of oxygen, and we also have for the silicon. Show quality chapter 3, CJ silicon. We have a lot of carbon coming from the graphite heater. We have a lot of oxygen coming from the oxide container of the silicon. So we have a lot of oxygen. So this oxygen here we wanted it to be 15 to 20 parts per million oxygen from the silicon wafer. Then we do this high temperature process to grow 50 to 100 nanometer size silicon dioxide, silicon oxide nanoparticles. So around those nanoparticles, around the silicon oxide nanoparticles, there will be a lot of dislocations. Now those dislocations, so the metal atom will go to the metal atom will go to the dislocations because the volume mismatch between the silicon oxide and silicon. So the metal will go to the defect around silicon oxide nanoparticles. So now look at how to make the silicon oxide precipitate. So there are three steps. There are three high temperature process. The first is the after diffusion with oxygen. So we know that we know that for the device. So this is the silicon. So this top layer here, we need it to be clean, no oxygen, and then no silicon oxide. So we have high temperature process. So that the oxygen come from here will go out, diffuse out. So oxygen inside they can move around, but this is okay. Oxygen on the top layer will diffuse out of the wafer. So this is called after diffusion of oxygen, so that the top layer here is clean, no defect. Then we do the nucleation process. This is low temperature, 700 or 750 degree for a few hours, and this will grow a silicon oxide 1 to 3 nanometer. The temperature is low, it grow 1 to 3 nanometer, because if the temperature is very high, the oxides they will not come together because they try to get dispersed. You will not nucleate. For the nucleation, we need relatively low temperature. So once the particle become 1 to 3 nanometer inside, they become stable. So when they are stable, we can have high temperature, 7 degree to grow big the silicon oxide. In the end, we grow them from 1 to 3 nanometer size to 50 to 100 nanometer size. Then around those oxide nanoparticles, there will be a lot of to trap the metals. As you can see here, the top layer here, this area here is the denuded zone because of this step after diffusion is on the top layer. This is the top layer clean. So no particle on the top layer is clean. So below you can see a lot of wet spots. So those wet spots, this is the silicon oxide precipitate. So the number of the wet spot is given by this step. The number is determined by the nucleation. You can see this is the pre-anneal time. Pre-anneal, this one is for the correspond to here, nucleation. So the longer the time, the more the numbers. So the size, the diameter is determined by this step, by this step. So you can see the longer the time, the bigger the diameter. So the diameter is determined by this precipitate, by this high temperature process. So the longer the time, the bigger they grow. That is how the trapping works. And now we look at how to measure the defect. So we can use the light. We can for the unpatterned wafer, we can use optical microscope, or we use the laser scanning to count the particles. For the light, we use the light. For the patterned wafers, we can also use light. We use optical microscope to compare a die with the good reference die. If we see the image different, so we know something may get wrong. We can also do the test structure. You do something like this. You can see this one is open defect. This is short defect. If you measure the resistance, between the pads, then you know whether there is defect or not. But this one is not very popular. For the impurities, we can use the material characterization method. So usually, I know you learn about characterization of the materials in your second year. So we have the excite by using electrons, ions, X-ray, or photon. The excite identify we look at the signals, then we count the concentrations. So the incident, the primary beam can be electron or X-ray or ions. This is electrons. The good thing for the electron is that it has good lateral resolution because electron can be focused very easily at good lateral resolution. So when the electron comes in, so we can detect AES. AES. So what is AES? A is OJ. OJ, so this is called OJ electron spectroscopy. OJ electron spectroscopy. This one is very surface sensitive. It's very, very surface sensitive because only the electrons, OJ electrons from the top surface, only from the very, very top surface can escape to form the signal. This is very sensitive to the surface. This one is detect electrons. So we can also detect X-ray. This is called XEX. It's called X-ray emission spectroscopy. This one is X-ray emission spectroscopy. A third one, we can also do the EDX. I think you are more familiar with EDX. It's also called EDS. It's also called EDS. This one also electron come in and you detect X-ray in the SEM. So we have EDX or EDS in SEM. This is called energy dispersive X-ray spectroscopy. Energy dispersive X-ray spectroscopy. So this one is most popular in research labs. So the incident can also be X-ray. Then we have if we detect electron, if the output signal is electron, this is XPS, X-ray photoelectron spectroscopy. X-ray photoelectron spectroscopy. This one is very surface sensitive. It's very sensitive to the top few nanometer surface because the photoelectrons, only electrons from the top can escape to form the signal. So we also detect X-ray. This is called X-ray fluorescence. X-ray fluorescence. If the incident is ion beam, for the incident ion beam, so we have two methods. One is called RBS, Rutherford backscattering. A second one is called SIMS, secondary ion mass spectroscopy. This one. So we have the primary ion come here. We detect and analyze the ions that is kicked out. And this is called the secondary ions. Okay, thank you.